you might get into medical physics if that's what you're interested in, and some of the kinds of things that we do in our workplaces. And the second part is about some radiation incidents, some practices and some real world experiences that I thought I would share with you, because you know, they're possibly some of the more interesting things that we get involved with. So I thought it's probably best I would put up what I've done in medical physics, and this is probably a you know, a reasonably typical example of someone coming and doing a career in medical physics, and to kind of illustrate the opportunities and the education and training pathways that we have. So you might want to ignore the dates, or at least not work too carefully on how old I am. But the A levels, I did physics, chemistry, and maths back in 1990. And so the fairly classic science combination, Bachelor of Science in physics, and then back in those days there was a training scheme run by the IPEM, the Institute of Physics and Engineering in Medicine, a basic training scheme which included a MSc in the workplace in medical radiation physics, and I finished that basic training in '95. So again, back in those days, there was higher training for a couple of years. So if you think for post-graduation, you've got a 4-year training program to become a medical physicist. So today I'll talk a bit more about this as the slides go through, but we do an STP, Scientist Training Program, which is 3 years long, and that replaces those 2 IPEM schemes there. So today, if you left in 1993, by 1996, if you were on the STP program, you would be eligible for registration as a clinical scientist. So then I've got a number of specialist certificates, and again, if you work in medical physics, many people will do the medical physics expert qualification here if they want to move up to the pay scales in medical physics, and then there's these other qualifications: radiation protection advisor, radioactive waste advisor, and laser protection advisor. And they're not academic qualifications. These ones, they're experience based. And they're based on demonstrating competence in a number of specialist areas. So, so a little bit easier to get those while you're at work. So then, for me, I spent 10 years in the NHS in diagnostic radiology, radiation protection, and nuclear medicine. Went out to Qatar for a few years. So again, this is a kind of opportunities that might be open to you. In medical physics, you can go, you know, quite often see adverts for jobs abroad, particularly I would say Australia, New Zealand come up quite often in the UK adverts, and some opportunities to do that. And I worked again in the NHS between 2007 and 2023 in radiation physics. And my current role in the Integrated Care Board started this year. So this is outside of medical physics, the kind of other scientific jobs that might be available to you. So you can see on the right-hand side here, the physical sciences in orange is the kind of pathway I've been going in here. So we've got all our physics options, but also options in engineering to come and work quite closely with patients, perhaps designing wheelchairs, specific communication devices for people, service users in an engineering context. If you've come from a biology or chemistry type background, then some of these life sciences and clinical physiology might be more of interest to you. So you'd be working in a lab, doing diagnostics on blood samples, maybe preparing slides to look out under a microscope and doing diagnostics for cancer and other illnesses. So there's a fairly common theme throughout all of these, scientific areas, which is that we're heavily involved in diagnostics. So the statistics, I think, are that 80% of all diagnoses that take place in the NHS are backed by a healthcare scientist of some sort. And these four roles here that we can see cover all healthcare science roles. The bottom one in blue, informatics, is fairly new, but I think if we were doing this talk in 10 years' time, we would be talking much more about bioinformatics, genomics, so biological computing, and how do we take our medicines and maybe customize them more towards our individual DNA for our patients. So it may be that I need a different therapy for my illness than somebody else, and our genomics systems will be the things that we need to achieve that. So that's heavily tied in with computing, and you can see really then a nice link between all of those scientific areas there. And I put these up in case we've got anyone from universities or schools on the call today. Many other careers in the NHS that you can do with a scientific background. There is quite a big list, so it's a good employer, I think, for people who are interested generally in science. So where did I work in particular? So my particular specialties, as I said, were in radiology, physics, and nuclear medicine physics. So in radiology there, obviously we're using X-rays. We've probably all had an X-ray at some point in our lives to view inside the body. And X-rays can include our sort of general X-ray. You know, I've broken my arm, so I have an X-ray to look at the fracture, all the way through to more complex types of imaging, such as CT scanning or maybe fluoroscopy machines, which can view either cross sections through the body, three-dimensional reconstructions, or in the case of fluoroscopy, moving objects. So if you want to see, I've got a problem with swallowing, for example, you can take a video X-ray of me swallowing something and see what the problem is. The muscle's not working quite right. Why is it that I can't swallow things properly? So that's X-ray. In nuclear medicine, we inject radioactive materials into the body, and these are labelled onto pharmaceuticals. So the areas that the pharmaceutical seeks out and sticks to will then glow, if you like, and our gamma cameras will be able to pick those up. So you could see a concentration, for example, on a bone scan where I've put an agent that sticks to the bones with some radioactivity. I can see areas where maybe I've either fractured my bones or perhaps I've got a secondary tumour growing there. So a typical day in diagnostic radiology might involve doing quality assurance measurements on some of these machines. So our understanding shows us that there's a small risk associated with each X-ray that we take of a patient, but also there's obviously a benefit. So we need to make sure, are we balancing out correctly our radiation exposure that we give with the kind of image quality that we get. We don't want a superb image quality. We need enough image quality to be able to do our diagnoses. And the job of a physicist then will be informing that balance. In radiation protection, we might be talking to colleagues about radiation legislation and how to be safe. So we do a lot of engagement teaching and training with people. And over here on the left, you can see a calculation, for example, using a software package to work out what the radiation dose has been, in that case, from a CT scanner. So you can see you've got a mathematical phantom, which is looks like a human, and you can see where the CT scanner has irradiated the body. And on the right hand side there, under organ doses, it tells us what the radiation dose is there. So in nuclear medicine, again, we do a lot of quality assurance. We need to make sure our devices are working correctly and safely for imaging our patients. And also in nuclear medicine, we do therapeutic work. So we might give somebody a fairly high dose of radioactivity to treat a tumour, for example, and a fairly common one is at the top there, iodine therapy. So patients had had thyroid cancer. Surgeons removed the thyroid gland, and the physicist then might be involved in giving a very high dose of radioactive iodine to the patient, which would then remove any remaining bits of the cancer that have been missed during the surgery. So we're aiming to really cure the patient completely of that cancer. So in nuclear medicine, you're working quite closely with patients, quite often face to face, delivering therapies, and talking to them also about the risks associated with those therapies. So I thought this was just a nice little, I won't do too long on this, just a nice little clip of the inside of a CT scanner, if you've never seen one of these before. So we can see, or you could see, the X-ray tube and the detectors there. And I think this is just to show for any people who aspire to engineering on the call, just how amazing some of the medical equipment we have in hospitals today is. So you can imagine all the equipment on that gantry there. I would imagine weighs must be at least half a ton to a ton, and you can see the speed that it's rotating at there. And of course, that's essential to have that very high speed so that we can get the images that we need in a shorter time possible. So we freeze any movement that's going on inside the patient. Okay, so just to finish then, working in the NHS, I think it's a nice summary here. If you like, helping people, using your science skills every day. You know, one thing that really attracted me to medical physics was that I would be using my physics knowledge, my degree, in an everyday context, really applying it and applying it to something really good. You know, we can make a big difference in our jobs to the outcomes that patients have and be, you know, really closely involved in their diagnostic and therapeutic processes. Always problem solving. No 2 days are the same, and it's very common to come into work thinking that you're going to be doing one thing and to suddenly find that you're going to be doing something else because things come up and you need to deal with those issues. And when we look at radiation incidents in a minute, we'll see some examples of that. It's a nice mix, I think, of practical work and working, sitting in front of a computer. Maybe it will be a scientific computer, a treatment planning system, for example, where you're planning your radiotherapy exposures, or maybe it will be a normal computer, you know, where you're preparing spreadsheets or presentations. And you also work in a multidisciplinary team, and I think that's a really nice thing. You know, you might be in a team with doctors, medical staff, nursing staff, allied health professionals, so radiographers, perhaps dietitians, all working together with the patient in that pathway towards their own treatment and diagnostics. So these slides, you know, courtesy of Joanna Sillers. Thank you, Joanna. I like the slide there. And just quickly then, the routes in to medical physics and other healthcare sciences. So we've got on the left-hand side, we've got apprenticeship schemes, which are at level 2 and 4. So you can, in fact, direct entry into the services from GCSE level in those apprenticeship schemes there. You can come in to a degree level program. So this would be post A level. That's the purple box as a healthcare science practitioner. And again, that's direct entry. Or you can come in after graduation into a level 7 program. So that's the yellow box on the right, training up to be a clinical scientist. And that was the STP scientist training program I spoke about before. Now, there's all sorts of other routes. You know, if you're already partway through your career, you can undertake equivalence processes in the workplace, perhaps. So instead of going through a formal degree, you might already have a degree, and then you can come into one of these areas in the workplace and do your training there. So I think there's quite a lot of flexibility there to do that. So there's a brief summary of apprenticeship schemes. The nice thing about this is it's all really well signposted online. I think there's a little link at the bottom there to the Institute for Apprenticeships, where you can find out more about these apprenticeship schemes if they're of interest to you. And I thought it's just worth including a little bit about salaries. So that's the full range of, if you like, professional salaries, excluding doctors and managers, but in the NHS, and really you might have scientists working on any of these bands. You know, you could have apprentices who might start around band 2 or 3. You might have a clinical scientists here at around band 7. Technologists maybe bands 5 through to 8A, and then you know, if you think maybe a head of section, head of service would be round about 8D or band 9 there. So the salaries, I think, are quite competitive. So there's some really good information available if you want to find out more about any of these things. We have a network which is online. It's completely free to join, and there's a little QR code there, or you can email me or Sonali, and we can give you access to the network. So if there's any time, I can show you a bit of that. But basically, on that network, there's a lot of careers type information. So if you want to find out more about coming into medical physics or one of the other sciences, then there's a lot of information on there for you. And there's also all the other things there you can see. So there's a lot of, for people already in the professions, around about, I think, 150 CPD sessions on there. So there are presentations, online presentations. You can go to conferences that have occurred in the past and watch the presentations from there, and there are slides, PowerPoints, things you can download, and we've got things that you can actually pick up which will be of use to yourselves. So if you want some mentoring, for example, you can ask to join our mentoring program. Again, it's completely free, and we've had some really nice success stories there. We've paired up some senior managers with some people outside the NHS working in finance, for example, to kind of cross learn some skills there. We've got people all the way back to A level who are meeting some of our people in our laboratories to find out, you know, I love biology, I'm really interested to come into pathology, and we've got those links made up through the network to get them the mentoring so that they can come on into a career in the NHS. Okay, so on to the second section here. I think there's about 15 minutes left. Sonali, am I right?
Yes, that's correct.
Yeah, okay, great.
A little bit more.
Okay, that's fine. Yeah, good. and just to leave some time for questions and things at the end as well. So so I thought, again, the reason I'm talking about this was just to illustrate some examples of my own field, working in radiation protection, some of the interesting things that we get to do in the workplace, and some of the maybe more unusual things. So with radiation accidents and incidents, unfortunately, they do happen. And so what you find if you work in a medical physics department, particularly in radiation protection, is you might be involved in the response team to deal with some of those incidents. So there's a national scheme, for example, the National Arrangements for Incidents Involving Radioactivity. So under that scheme, the police can instigate a NAIR incident. They'll call the NAIR responder, who might be the physics department at the hospital, and the physics team or the NAIR responders will then decide, okay, yeah, we're up for this. We can handle going out to deal with your particular incident, or that one really sounds a bit too tricky. There's a really big nuclear problem. We're not experiencing that field, so we need to stand down and send that on to somebody else. So so you might be dealing with external incidents like that, but also in a physics department, internal incidents. So you may have incidents that happen in the hospital, either with radioactive substances or with radiation machines. But you also might have people that come into your hospital. So if there's been an accident, for example, involving radioactivity, people might be contaminated. They could potentially start coming to your hospital either via the ambulance service, or they'll be walking wounded. They'll turn up, and then your physics department will need to be ready to respond to that. So we have two scenarios. I think we've got practices. How do we make sure we're ready if it happens for real? So that would be an exercise. And then we have real incidents, so things that really happen, real radioactive substances, and we have to deal with those. So we'll just talk about a couple of those today. So this first one is an exercise. So just to be very clear, this didn't actually happen. This was an exercise that was run with the hospital. We had the fire and rescue service involved, the ambulance service, the police, the Environment Agency were involved because there was a radioactive elements. We had the press involved, the press coming along to try and see how much information they could get out of people, and it was really a big exercise that was run to try and test out what might happen if things went wrong for real. So the exercise was designed by an NHS team working with the Fire and Rescue Service, and we were told we need to think about shark-infested custard. For those not familiar with that term, it needs to be terrible. So if you have a group of let's say physicists and doctors, ambulance and fire and rescue, and they're doing really well, they've got everything under control, you need to be able to make things even worse for them to try and test their full capabilities. What happens if things get really bad. So this is the scenario we had. We've got a theatre with some radioactive sources in, and a patient, and we've got a nuclear medicine room here. This is one of our iodine patients who had swallowed a capsule containing iodine, and that was now liquefied inside the body. So every time that patient goes to the toilet, the urine is very radioactive. If they're sick, that would be radioactive. So there's quite a lot of hazards from that patient there. So what happened was a fire started in the control room. So I put this slide up in a conference that I spoke up, and there was this deathly silence in the room until I explained that actually this is a simulation that the fire brigade did for us. So they took some photographs around the hospital, and they put their own fire on things. They didn't actually come and set fire to the hospital, which is a big relief. So this is the scenario then here. Patients and staff were evacuated from the areas, but 2 patients were left behind. So that was the radiotherapy patient who was anaesthetised, connected to an anaesthetic machine in the theatre, and the nuclear medicine patient who was pretty immobile and had also had their capsule in the morning, so they were at their most radioactive. So as usual with these things, it all got worse. There was more fire, and the fire started to spread. So the teams evacuated the radiotherapy patient, and there's a special ambulance team there called the Heart Team. I can't remember exactly what it stands for, but hazardous. They can basically go into confined spaces. They can work at height. They can work with breathing apparatus in a fire environment. So they're a really highly skilled paramedic team that can get into places that other people couldn't. So unfortunately, the patient was evacuated, but half of the seeds were left in the trolley in the theatre. That's radioactive seeds in the radiotherapy theatre there. And the fire, of course, spreads in there. And so, but also spreads towards the patient in the nuclear medicine room. And you see it spreading down the corridor there. So the nuclear medicine patient was evacuated as well, and unfortunately suffered a cardiac arrest and was incontinent while they were being evacuated. So that meant that there was then contamination all over the fire and rescue personnel. Remember, this is really quite a high level of radioactivity. So we needed to deal with that. But also, the patients in cardiac arrest, how do we deal with that life-saving scenario? Do we take them to the accident emergency department, bearing in mind they're highly radioactive and contaminated? So it was quite a tricky thing for the teams to really get onto and think about, very quickly how we're going to manage this developing situation. So we've got contamination on the floor now, radioactivity, and the fire and rescue service using water, which then spreads the radioactivity all around the ward area. So you've now got a large area of ward contaminated, and the fire's gone into the radiotherapy theatre. And remember, our radioactive seeds are in here, which have now caught fire. And so you've got airborne radioactivity as well. And if you don't turn off your air conditioning system to the hospital, and of course this is one of the things we needed to test as part of this exercise, that radioactive smoke will then be passed around the entire hospital. So you could end up with that going into wards and other areas in the hospital via the air conditioning system. And that was the photograph of the first physicist to arrive at the scene there. So you can see, it involves a lot of people. It's a really good chance to test things out. I think in reality, you'd be highly, highly unlikely to have something as bad as that. But, it did give people a chance. They look like they're enjoying themselves far too much. It did give people a chance to really think about how we would work together in one of these scenarios. And just to give you a flavour of the kind of issues that came up, with a contaminated patient, the nursing staff were saying, we're not sure how we would decontaminate these people, and the fire and rescue service said, well, we can show you what we do if you want. So they got one of their colleagues and they fetched one of their fire hose, and they hosed their colleague down with around about 500 litres per minute of water, which of course removed the contamination, but would not be the kind of thing you'd want to do with a sick patient. So, and it's an example, I think, of why it's good to get all of these different teams together to think about really, what is the best way to do things. Okay, so just to finish on then, just a couple of real incidents to show it does happen for real. So this was Tunbridge Wells, lovely residential road in 2009, and we had a call. It was from the NARE incident, the national arrangements that I spoke about earlier, to say that somebody had dug up a radioactive container in their garden. So by the time we got there, they'd already been visited by 6 fire engines, which you'd imagine caused quite a bit of concern amongst the other residents of the road. Again, another learning point for everyone. They gave us the wrong information. So they told us that the dose rate from this particular article was 100 microsieverts per hour. So I was talking to them very quickly about potentially needing to evacuate houses in the adjacent to this building, and then they corrected that and said they were a factor of 1,000 out, and it was actually 0.1 microsieverts per hour, which really wasn't a big problem. So so you can see even in real incidents things go wrong. So what happened there? We did some monitoring. There wasn't any detectable radioactivity, and the capsule you can see here, or the tin, was carried away, taken away to Dungeness power station, where they got all the robots and things to have a proper look at it. And this one was 2011. So I was looking forward to an evening at our children's school, going to a barbecue, and we had a call again from the NARE team to say the police have arrested somebody, and while searching their house, they found a lead pot full of radioactive things that have come out of smoke alarms. So I went down to the police station, and these are the photographs here. So you can see, we've used plastic, for example, to put on the table to make sure that we're not spreading contamination. And it was really a good job that I did this, because actually these were quite old radioactive sources, and they were starting to degrade. So we're starting to lose little bits of radioactive chips from the front of the source, and they were falling onto the plastic here. So so what I imagined would be a 5-minute job disposing of a couple of smoke alarms turned into 3 or 4 hours with the careful testing and making sure there was no contamination in the area afterwards. And you can see on the bottom right hand side there that you're getting quite a high reading from the source there. And our lovely device on the left here, which is telling me it's americium-241, which is a radioactive substance, and that's exactly what you would expect to have on a smoke alarm. So we've got some pretty nice instruments available to us to tell us. So you can see the one on the left. Now I know what the type of radioactive substance is, and that tells me that I can use this device here at the bottom right, called a scintillation detector, and that's very, very sensitive to the gamma emissions that come out of our americium radioactive substance. So I knew that I'd be able to use that to do the checks after the decontamination. And I think that's me done. There's again the QR code there. If you're interested in joining the network, you can scan the code there. And otherwise, I'll hand back to Sonali, see if there are any questions or comments.
Thank you very much, Mark, for the informative talk on your journey so far within the NHS and your career, as well as the radiation incident.